It's time for another amazing chemistry video with Mr. Stapleton! Proudly sponsored by Farming Junior Nice Coffee.
Hi guys, welcome back to my next video. For today I'm going to be doing some more titration calculations, hopefully give you a bit more help in terms of doing them if you're struggling. So the first thing I'm going to be doing is just a really simple one, just to go back through those 6 steps. Okay, so we're going to be doing a reaction between carbonic acid, H2CO3, and sodium hydroxide. Okay. Now, what we're going to be doing is going to be taking some 0.152 moles per litre carbonic acid, okay, and we're going to be titrating that against 20 mils of our sodium hydroxide solution. Okay, so first step is always the balanced equation. So carbonic acid plus sodium hydroxide, acid-base reaction, so we get a salt, which is sodium carbonate, and we get water. So we balance it up, 2 there, 2 there. So remember, that's really important so we can get our Molar Ratio correct later on. So what we did when we actually did this titration was we got a number of different titer values. Okay, so I'm just going to go through that because I want to make sure you guys understand what concordant titers are. So anytime you're recording your titer values, you should set up a table. So we've got final, initial, and then the titer value. Okay, so we put the final on top because then it's just a simple case of doing some subtraction. So for this one we did 4 titrations. Okay, and these were the values that we got. So 21.25 starting at 0.00. Then we started at 21.25 here, just following on, went to 42.55, we started at 1.00 here, went to 22.40, and we started this one at 22.40, and we went to 43.75. So what I wanted to point out in this is to make sure you remember that when you're reading your burette, you can always read to 2 decimal places, okay? So make sure you do that in your calculations or when you're recording in your titrations, okay? Really important. So we're going to get some titer values here of 21.25, 21.30, 21.40, and 21.35. So having a look at our titers across here, okay, remember concordant titers are ones that are within plus or minus 0.1 milliliters of each other, okay. So having a look through here, these 3 are within 0.1 of each other. The lowest is 21.3, highest is 21.4. So there are concordant titers, they're within 0.1 of a mil. This one is out, all right, by 0.15 from that highest value. So we're going to discount that one. Now, what's really important to notice is that if you went through and look this way, 21.25, I'm going to use a different colour for this, and if we went 21.25, this one, 21.3 and 21.35, they're within 0.1. Okay, but what I've done is I've actually discounted the first titration because the first one we generally tend to use as a rough titration. Okay, and so in this case where we've got 2 possible options within 0.1, we go with the next 3 on the assumption that practical technique's a little bit better and we're going drop by drop a bit more easily in those 2nd, 3rd and 4th ones. Okay, but I'm going to choose those 3. So averaging out those 3 gives me an average titer value over here for volume, okay, of 0.02135 litres. So I just wanted to make sure I covered that in terms of concordant titers, made sure you understand what we're looking for and what to do when you've got a couple that match, okay, within 0.1. So there's our values, okay, that's what we know, that's step 2. So now we go to step 3, which is calculating number of moles for our known solution. So our number of moles of carbonic acid, so remember if you actually use your little subscripts like this, it makes it a lot easier. So step 1 was writing our balanced equation, step 2 was writing down what we know, step 3 is our number of moles of carbonic acid. So N equals C times V, so it's 0.152 times 0.02135. Okay, so if you work that out, you get a value of 0.00325, 0.0 0.0325 moles. Okay, that's step 3. Step 4 is now our molar ratio, or a mole ratio. So our unknown is on the top, sodium hydroxide. Our known is on the bottom, our carbonic acid. So getting this from the equation at the top, 2 in front of the NaOH, 1 in front of the carbonic acid. Okay, so our mole ratio is 2/1. So in step 5, the number of moles of our sodium hydroxide, our unknown, is 2/1 times by this value right here. Okay, and so that actually gives us a value of 0.00649 moles. Okay, these values aren't too important. We leave them on our calculator so we can use them later. So the last thing we want to do is calculate our concentration of our sodium hydroxide. That's what we're doing this one. So C equals N/V. So it's this value up here, 0.00649, divided by our volume up here, which is 0.0200. Okay, and we get a final concentration of 0.325 moles per litre. Okay, I've done that to 3 significant figures, which is the same as what I had up here in my initial concentration and the volume that we pipette out of 20.00 mils. That's 4 significant figures. So our concentration was the least accurate, 3. So that's how we do it. I've gone through pretty quickly because I've gone through that in the previous video, but hopefully that's just a refresher of those steps that we do. Okay. Now what I want to do is show you a slightly more complex titration, okay, which is what you tend to get a little bit more of, because that's a very, very basic one. Okay, and hopefully this will give you a little bit more of an idea of how to start problem solving in your head. Okay, so this one, it's probably easiest to show in a little bit of a diagram form what we've done. Alright, so we've got some benzoic acid, okay, and we're going to be making it up into a 1 litre volumetric flask. Okay, so here we've got a 1 litre volumetric flask, 1000 litres, and we're dissolving in 1.090 grams of benzoic acid. Okay, now you don't have to know the formula of benzoic acid, something like that they'll give you in the exam. So the formula is C6H5COOH. Okay, so if you go through and follow your normal molar mass calculations from the periodic table, right, 7 lots of 12.01. Okay, so I'll actually make sure I show that too. So 7 carbons, so it's 7 lots of 12.01. Alright, we've got 2 oxygens, so it's 2 lots of 15.999. Okay, and we've got 5 there, another 1 there, so 6 lots of hydrogen, which is 1.008. Add all those up and you get a molar mass of 122.18 grams per mole. Okay, make sure you can do those, they should be bread and butter for you. Okay, now what we do is we make up our standard solution, okay, and then we take 20 mils of that into our conical flask. Now what we also do for that is add 75 mils of sodium hydroxide in there. Now the reason we do a titration like this is we assume that this benzoic acid is actually pure, and what we're trying to do is actually determine if this benzoic acid is all pure or if it's perhaps decomposed or reacted with something else as well. So we're actually trying to do a percentage purity titration in this case here. Okay, so our sodium hydroxide in here is going to react with our benzoic acid. Okay, and the first thing that we would have needed to have done is worked out how many mils of sodium hydroxide that we should have needed as a minimum. Okay, so what I'm going to do is I'm going to go through firstly and do the benzoic acid calculation here, just to assume how many moles we should have had of benzoic acid if it was pure. Okay, so I'll come back to that diagram. So our number of moles of benzoic acid, so I'm just going to put benzoic acid here, all right, is mass over molar mass. So it's 1.090 grams over 122.18. So in theory, what we've got in our conical flask there is 0.008826 moles of benzoic acid. Okay, that's if it's 100% pure. So what we want to do, right, is check out how much of this actually reacted with the sodium hydroxide solution. Okay, so that's our number of moles of benzoic acid. All right, and in this video you might need to go back and rewind this to have a look at some of the calculations, because I'm just going to be rubbing them out as I go. All right, and you can copy them down as well. All right, so that's our number of moles of benzoic acid. So I'm just going to write this up the top here, so we keep that value in our heads. 0.0088826 moles. That's what we were expecting. Okay, so we had this many moles of benzoic acid that we put in. Alright, so what we need to do is work out how many moles of our sodium hydroxide reacted with it. Now that's not easy to do, but what you've got to remember is that we put in 75 mils of our sodium hydroxide. Now, some of that reacted with the benzoic acid, which means we have the excess or the leftover, okay, that is unreacted. That's the stuff that didn't react with the benzoic acid. So we find that out via titration with sulfuric acid solution. So sodium hydroxide plus sulfuric acid solution, okay, giving us sodium sulfate plus water. Balance it up with a 2 there and a 2 there, okay. So our sulfuric acid had a concentration of, and I just need to find this, sorry, 0.00430 moles per litre, and our volume was 19.1 millilitres. That was our average titer value. Now, if you go through and do this calculation, and I'm not going to do it for you, what you should actually find out is that you get that the number of moles of sodium hydroxide, okay, that reacted with sulfuric acid here was 0.000164 moles. Okay, so I want you to double check that you can do that. All right, calculate number of moles of sulfuric acid, molar ratio of 2 to 1, double it, you should get this value here for number of moles of your sodium hydroxide. Okay, so that's really, really important to hang on to. So I'm going to move that up the top. Okay, up here. So we had the number of moles of sodium hydroxide that was unreacted was 0.00164 moles. Okay, so what we can do now is work out how much reacted with the benzoic acid. Okay, so for the benzoic acid, initially, remember, we put in 75 mils of 0.00350 moles per litre sodium hydroxide solution. Okay, so initially what we put in, number of moles of sodium hydroxide, was C times V, so 0.00350 times 0.075, and we added in 0.0002625 moles. Okay, so that's how much we had in initially. We know that up here we had this much that was unreacted. So if we take away 0.000, and I missed a 0 up here, sorry, 0.0001640, if we go through and take that away, we will work out that we had left 5, 12, that's 8, 1, 15. So we had 0.0000, I think I said 4 there, 985 moles that reacted. Okay, so we know that we had 0.000985 moles that reacted, okay, up here with the benzoic acid. Okay, so what we've calculated is that we have, and if we come back to this, okay, really important to remember this, okay, so we had 1 litre of benzoic acid that had 1.090 grams dissolved into it, okay. We took 20 mils of that into our solution. We put in our 75 mils of sodium hydroxide. From that, we have determined that 0.0000985 moles of the sodium hydroxide reacted. Okay, so what we can work out is what mass of benzoic acid was in here, and then if that relates to the final amount up here. So I'll show you what I mean. To get our mass of benzoic acid, and I apologise that my voice is starting to go, mass equals number of moles times molar mass. So 0.0000985 times by the molar mass that we determined earlier, 122.18. Okay, all right. we can work that out. So that tells us that in that 20 mils we had 0.012 grams of benzoic acid. But what you've got to remember is that that was only in 20 millilitres, and that we made up a 1 litre standard solution. Okay, so in 1 litre there's 1,000 millilitres, so 1,000 divided by 20 will tell us the ratio. We times that by 0.012. And we get 0.602 grams. So what we can actually see now is initially, and I'm going to bring this back over here, deliberately on top, so we put in 1.090 grams of benzoic acid, or what we thought was benzoic acid, okay? But we've actually only got 0.602 grams in there. So our percentage purity, which is what we were trying to find out right at the beginning, is 0.602 over 1.090 times by 100. So we have 55.2 percentage purity. And that's it. I know that one's quite involved. Go back, have a look over it. Hopefully it makes sense for you. Thanks guys. Bye.